If we do stay on schedule to have your unit exam next Wednesday, then that means that Monday after class, whoever wants to can track on down to by my office, the chemistry lab, and we'll have a review session. Okay. If we don't get as far as we need to, and we bump the test, I say it's like a democracy. I ask you, should we bump the test to Friday? If it's bumped to Friday, then after lecture Wednesday will be the review session. Okay, not everybody can make it. Remember, we're going to record it and make it available. Any questions about that?
Can we vote now?
No, we cannot vote now. Did we talk about these pictures? Did we kind of already talk about these yet?
Yeah. Those are last ones.
Okay, good. Okay, so the next concept we need to talk about is actually a scientific model. And scientific models are notorious for being, they're not really the way it is, a scientific model, but it's something that you can hold in your hands or mush around in your brain. You're like, oh, okay, that makes sense. So this scientific model, and I brought one that's kind of broken here today. It's called the celestial sphere. This was here before I got here, like 15 years ago, 10, 15 years ago. And so you see it's been, dropped a few times. But just ignore that. This is a celestial sphere. Can you see the yellow dots? Okay, and if you were to look a little bit closer, you can kind of see constellation names. I guess it's upside down. Oh no. Okay, there's okay, so the dots are stars. Now this isn't really the way our part of the universe really is. It is not such that all stars are the same distance from us. That is totally not the case. But actually, see the center is the Earth. There's a rotating thing. I can spin the Earth, okay, and as I spin the Earth, if you were on the Earth, it would look like the stars are moving. So there's the Earth in the center, and I can kind of spin that, okay. And actually, the stars do appear to move throughout the course of a single night. The stars do. That's Polaris. They go counterclockwise around Polaris in our hemisphere. And I kind of talked about if you take the circles, make them wide enough, you end up rising in the east and setting in the west. Okay, and then they kind of go over there to be something a little different. So this is the celestial sphere. It's a hollow ball with the Earth in the center. Okay, so we have a few important things on the celestial sphere, important aspects of the celestial sphere. The celestial sphere, I love saying that, actually has a north pole. So this is the north pole of the celestial sphere. It lines up with our Earth's north pole. This is the south pole of the celestial sphere. Okay, the celestial sphere has an equator. The way this is, can you kind of see the ribbon there, like around the Earth's equator? If you were to extend that out, actually it coincides with where these two hemispheres on the celestial sphere are joined. So this would be the celestial equator, okay? Lines up with Earth's equator. The other thing is, can you see where it says, let's see, March, April, May, those dots with numbers? Those dots with numbers actually are where the sun appears on the celestial sphere that time of the year. And actually, this part is broken. Yeah, I can dial in, what are we, the 25th? What's today's date? August 25th-ish or so. So there's the sun on the celestial sphere. Okay, now this is not the way, this is a model, okay? So it works pretty good. And the sun will, are you guys anybody into astrology a little bit? I dabble, I don't dabble. I look at my horoscope, just out of curiosity. But astrology, not astronomy, astrology goes with like where the sun is against the background stars. And so actually you can see there's August, September, October. So the sun is going to move against the background stars. It will, as the Earth orbits the sun. That's the celestial sphere. Okay, so here actually, on the next page, is a picture of the celestial sphere. So we could do a little bit of spinning there, and it looks like the stars are moving around somebody who's stationary. But what really is happening is the Earth is rotating on its axis, and that causes things to move in the nighttime sky or the daytime sky. So you see the light blue is the celestial sphere, the Earth in the center. the Earth's axis of rotation extend out to intersect with the celestial sphere. That's the celestial north pole, celestial south pole. The Earth's equator extends out to the celestial sphere, and that's the celestial equator. Okay. So just keep in mind, like I'm sure you already know, that, like, for instance, if we pick on, I think this is the stars in Perseus, the constellation Perseus. Okay. If we pick on Perseus, what looks like it's all the same distance from the Earth is really not all the same distance from the Earth. It's an assortment of distances. I said that actually you can look at the sun throughout the course of the year against the on the celestial sphere, and it is actually tilted from the celestial equator. And some of you are already familiar with this important angle. This angle right here is actually 23.5 degrees. Okay. All right. Okay, so this chapter is all about what do you see in the nighttime sky. So one of the things we can see in the nighttime sky is the Milky Way. And the Milky Way got its name because it kind of looks like spilt milk. But I think we've already talked about the Milky Way a little bit. Galileo used binoculars to look and see that actually what looks like dust is really tiny, tiny little stars. So when we look at the Milky Way, actually we're looking into the plane of the Milky Way galaxy. Okay, so we said our cosmic address is, our sun is just a star, one of 100 billion stars on a frisbee with a frisbee worth of stars we call the galaxy. So if you look one direction, you're going to kind of see the disk part of the galaxy. Another direction, you see that. Okay. So if you're ever looking at a figure like this, so this is the Milky Way, and you think this is the disk part of our galaxy, that should be like hopping with stars, and it is hopping with stars. Then you might wonder, well, there's these dark regions. You're like, really? What's those dark regions? And it's not absence of stars. It is actually these kind of dark, cloudy regions right here. Okay? They are there because there's dust there. There's dust that blocks your vision to see stars beyond them. Okay? And actually dust, we call that what? Nebula. These are dark nebula. Within the disk of our galaxy, or plane of our galaxy. Okay. So the local sky basically is, if we step outside this door, okay, our view is obstructed by buildings. But if we were in the middle of a field, it would work better. And if we look around our horizon 360 degrees and look above our head, we have just seen our local sky. Now, we could relocate it. We could get in our car and travel, 30 miles south, get out of our car, look around, we'd have a different local sky. So your local sky depends on where you are on the Earth, okay? We can describe our local sky in terms of altitude, okay? So when you guys are doing, this might be important for your lab write-ups. The moon has been beautiful, by the way, and the weather's been awesome, so I hope people are kind of grabbing binoculars and looking at the moon and trying to formulate something that you can turn in as your lab report. But one of the things I want you to do is to say what the altitude is of the moon. And you just need to approximate that. And in a minute, I have a slide that says basically, if you hold your hand out, this amount on your hand is 10 degrees, okay? So, for instance, that's a good example. If I go over here and hold my hand out and try to see like how far up that clock is, looks like, see, 10, 20, 30, about 40 degrees. So that clock is about 40 degrees. Okay, so that's how that works. 40 degrees of latitude, that's what that is. The other thing to describe where the clock is or whatever was we kind of need to say where is it direction-wise. And so the example here is if this chick, this gal in the middle, is pointing to the sun, And the sun is right here in her local sky. Okay, see, there's the sun. I don't know if you can see it. There's the sun in her local sky. So she would say the latitude is 60 degrees, okay, and the direction of it is southeast. Now there's also, you can kind of do directions different ways. But notice that this is due south, okay, north, okay, so this would be between south and east, southeast. So that kind of pinpoints where the sun is for her at that particular time. A few other things about your local sky. The zenith is right overhead, your zenith. Kind of related to your zenith is the meridian. Let's see, what did we say? This is north, right? That's Polaris, and that's south. So our meridian would actually go through our zenith, go due north through the zenith to due south. That's your meridian. I guess that's it. Horizon simply is when you go around like that, that's your horizon. So this is what I did a minute ago with kind of extending my arm and saying how high up is Polaris. And it's kind of coincidental that not coincidental, but how high up Polaris is, what Polaris's latitude is, actually that coincides with your, what its altitude is, coincides with your latitude. Have you ever noticed how close those words are together, altitude and latitude? Its altitude, about 45 degrees, that would coincide with where you are on Earth, your latitude. That's coming up in a minute too. So we have 10 degrees, okay, 20 degrees. I could have gone faster, 20 degrees, right? 20 degrees for this, and 1 degree for your finger. Now, one of the things I think is interesting, have you ever noticed where the moon looks humongous when it's rising or setting? Mostly when it's rising, because I usually don't see a setting moon. But the sun looks humongous, but it's just a trick of our minds. And you can prove that to yourself if you do this little exercise. So the moon is about 0.5 degrees. We say it subtends about a half of a degree, okay, half of a degree. So it's about a half of your finger. And you're like, dude, I so know the moon is bigger than that when it's rising, okay? But go ahead and check it out. So if you extend your finger, kind of squint at it, you know, the moon should subtend about half of your finger. Okay. There's a thought. All right. So it's also helpful to kind of know distances between objects. Like, for instance, here's the Big Dipper asterism. We have the handle part of the Big Dipper, and then we have the bowl part. Of course, this slide is kind of reminding us that we can use the bowl stars in the Big Dipper to find Polaris. Sometimes those two stars are called the pointer stars because they point to Polaris. But the point here is that the distance between them, the angular distance that separates those two bowl stars, is about 5 degrees. So let's see, that would be half of that, right? Half of that. Okay, Southern Cross, we don't see that constellation, but it'd be in the southern hemisphere. Okay, so just to remind you, a full circle is 360 degrees. Okay, and actually we can break a degree down into minutes. So there are 60 minutes in a degree, and actually we can kind of get even smaller than that, and there are 60 seconds in a minute. So honestly, you probably just need to worry about degrees, but there is that kind of fine-tuned angular thing going on. So this is kind of going back to something that you've probably been exposed to. You know, GPS, Big Brother watching you, that sort of thing. They can pin you down your location on Earth by coordinates, your longitude and your latitude. I think GPS coordinates are something different, though. I'm not sure. Okay, but your latitude and your longitude. So let's see. Here's my globe in here. So circles of latitude are centered on the equator. Okay, remember how this goes? So we're going north latitude here, south latitude here, but they are circles. Okay, they get smaller and smaller as you go towards the poles. What's this latitude up here? The top, what's the North Pole? What latitude is it?
0.
Nope, that's 0.
Oh, so.
It is 90. Yep, it's 90. Very good.
Oh, you have it up on the board.
Well, maybe. So this is 90 north, and this is 90 south, okay? And then there are lines of longitude. And I always kind of think long. Lines of longitude go like this. And I'm just fascinated by this. By just randomly, actually, this line of longitude is called the international date line. That is so crazy. Have you ever thought about that? Like, here you're one day, here you're the next day. That's how that goes, okay? The international date line. Opposite the international date line, we have over here the prime meridian, okay? So the 0 longitude is right here. Here's a 0 longitude, prime meridian. So the deal is from the prime meridian, you go east or you go west. And actually, we're west of the prime meridian. I looked it up. I Googled it. You can do everything on the internet. Maybe the answers aren't always correct, but you can get our longitude and latitude coordinates. At this pen tonight. Keokuk is, because this can be helpful sometimes, 40 degrees, 24 minutes north of the equator, and we are 91 degrees, 23 minutes west of the prime meridian. Okay, so there you go, that's Keokuk. So, actually, like, if you get any sort of software that you're trying to kind of a map of what the stars are like in the nighttime sky, it oftentimes will need to know your coordinates. A lot of times the application will have a data bank that has cities, and Keokuk is oftentimes in there. Okay. So motion of stars throughout the night. So you guys know the Earth spins on its axis of rotation counterclockwise. Make sure we get this right, counterclockwise. It also orbits the sun counterclockwise. Okay. And as it spins, that's why the sun appears to rise in the east and set in the west. And as it spins, actually, that's why the stars move throughout the course of a single night. And I mentioned this before. These are star trails down here. So if you were to be able to just set your camera and set it still and open up the shutter, you actually would see these little arcs made by stars. Okay. But notice they kind of have a bullseye appearance because they are all, one point that doesn't move for us in the northern hemisphere would be Polaris. That star does not move, plus or minus. So, stars that are close enough to Polaris, let's just pick on the northern hemisphere for now, because we have a star that is our North Pole is directed to. Stars that are close enough to Polaris, actually, if you were to be able to make a complete star trail, would make a complete circle. So here we go. Circle, circle, circle. Now, if that is the horizon, that's to say if this is the horizon down there, you can't have any more circles because even though they're moving counterclockwise around Polaris, they come up from the horizon and then they will set, okay? But the ones that I've drawn in, these guys right here, actually you'll see them all night long throughout the year. Those are what you call, and I have a slide coming up to say what they are, these are what you call circumpolar stars. Circumpolar stars. In the southern hemisphere, because of the Earth spinning, same Earth, right, in the southern hemisphere, actually their stars will go clockwise instead of counterclockwise. around, there's no star there to go around. Okay, just kind of I'll show you how they use the Southern Cross to find where their pole is pointed, where the southern pole is pointed to. All right. So circumpolar stars. So here we have, you can kind of see the celestial spheres, the blue orb around the Earth. Okay. Also drawn in here is that person's, there's one little tiny person there, and here in light blue is that person's local sky. That is his local sky. Okay, you can kind of see his horizons, you see the zenith overhead. Okay. Actually, then if he was looking for Polaris, he would find Polaris right here on the celestial sphere. That's Polaris. One of the things I have coming up on a slide, I think I've already mentioned, the angle that Polaris makes with the horizon, so here's the horizon, here's the angle that Polaris makes. That angle right there, angle, okay, that actually is equal to the latitude of the location. So for us, we should find Polaris about 4 fistful from our horizon. Okay? That's how that works. And when I say angle, I should say angle, i.e., we called that in your local sky altitude, didn't we? And the angle it makes with the horizon. Altitude. All right. So notice then, I like this figure because check out this little kind of swatch down here. I'll go ahead and make it green. This little belly of stars on the celestial sphere down here, these are stars that this person will never see at that latitude. One of the things we're going to see is that the latitude, let's go to North America here, okay, the latitude you're at kind of sets the stage for your local sky. Put another way, if you take 40 degrees, 24 minutes, and you go all the way around that circle like that, we all see the same local sky. We all see the same local sky, same latitude. Okay? Now, if I switch latitudes, okay, say I go down here to, let's go somewhere interesting. Okay, are these the Bahamas down here-ish? I've never been.
Yes.
Okay, oh yeah, duh, I must have probably saw it, but yeah. So if we go, instead of here, if we go south, okay, our local sky is going to change. So your local sky changes if you change latitude. Okay. When I was saying this right here, you know, the 40 degrees or whatever, we all have the same local sky. Notice what I'm changing here is I am changing longitude. Longitude. So for instance, I could skip along, find the international date line, okay, and as long as I am 40 degrees north of the equator, same local sky. It's kind of weird to think like that, but it's true. We'd have different time zones, okay, but the same local sky. Okay, so your circumpolar stars, check this out. All right, so, well, I'll get to it, I think. Your circumpolar stars, I'm going to come back to that. But for sure, when you find Polaris, you can use just however you want to use to take the altitude of Polaris in your local sky, and that will be your latitude on the Earth. Okay. All right. So I already kind of said down here in green, in your local sky, there are certain locations that you're never going to be able to see. But that varies with latitude. You change your latitude, you can see them. All right, so polar bear. So let's go to North Pole. Okay, see some northern lights. Okay, now at the North Pole, what degree is that? We said it was 90, right? So 90 degrees is where, with the horizon, is where we should find Polaris. So 90 degrees with the horizon is like that, right? Right there. That's an intersection of 90 degrees. Okay, so Polaris is straight up actually at our zenith. Okay, so with that in mind, if we're looking for how to make our star trails around Polaris, everybody look up. Look up, thank you. So look up and go counterclockwise, one circle, kind of close to Polaris. Then go counterclockwise another circle. Go counterclockwise another circle, close to, getting farther from Polaris. So basically you make ring after ring after ring of circumpolar stars. And then you get down to the horizon, and basically at the horizon you make, this is star trails, right? You make one big star trail. Okay. That's why this polar bear is going to get dizzy with his star trails, because basically it's all circumpolar stars at the poles. We only have circumpolar stars that go down to 40 degrees worth of circumpolar stars. That's where you see the full circle, full polar bullseye. Aside from that, you're going to just kind of see it part. All right, now let's go to the equator. So the equator is 0 degrees, okay? And if 0 degrees is your latitude, then 0 degrees should be the angle that Polaris makes on the horizon. Let's see, specifically the north horizon, right? Let me see, let me get my, north is that way, right? Okay. And I said looking west. Really makes a difference, but I'm looking west. Okay, Polaris, if I am at the equator, Polaris is just right out there, like on the horizon, okay? If I were to look at star trails from around Polaris, it would look like little half circles. The best I could do would be one little half circle. I can't even make a full circle. There are no circumpolar stars, okay, if you're at the equator. Then I make an arc, I make an arc, I make an arc. Oops, am I doing it the wrong way? I should be going counterclockwise. I make an arc, bigger arcs, okay? Then I finally kind of get to the whole due east, due west thing. And honestly, then I make just, the star trails would go from the east to the west. Okay, then they would make smaller and smaller arcs down to the south celestial pole, okay, down to the horizon. So that's kind of what we have going on. So actually, if you're facing either due west or due east, you're basically going to see the star trails going like that. Okay. And you have no circumpolar stars. Okay. No circumpolar stars. And this is all stars are circumpolar. And then the last example I have here is kind of in the mid-latitudes. What does that look like? Okay, and it looks like this over here, in this direction, over here, must be Polaris. And none of these look like circumpolar stars, but there would be circumpolar stars over that way. You just kind of see it slant like that. All right. So I've already kind of said as much, but your local sky will vary with latitude, where you are from the equator, but it won't with longitude, if you kind of go east and west of the prime meridian. Okay. So to kind of exaggerate that, we have two figures here. We have somebody at 90 degrees north latitude, and then somebody here at 34 degrees, I guess, south latitude. Okay, and their local skies are totally different. So look for kind of the dome of stars this person has versus the dome of stars or dome of sky this person has. It could be daytime sky or nighttime sky. All right, so a couple of figures, the northern hemisphere and the southern hemisphere. So the northern hemisphere, let's kind of look what's going on with this kind of time, sort of a time-lapse photo here. Not really a photo, it's just a figure. So here we have Polaris, and so we should look for counterclockwise motion. Remember, Polaris is actually the end star in the handle of the Little Dipper. And so that's what you're seeing. There's the Little Dipper. So this would be like position 1, position 2, position 3, and position 4 throughout the night. So the Little Dipper kind of swings around counterclockwise. So that means, well, the Big Dipper also swings around counterclockwise. So that's position 1, position 2, position 3, and position 4. Okay, it's also swinging around counterclockwise. But in each case, you can use, just like this figure emphasizes, in all cases, you can use your pointer stars in the bowl of the Big Dipper to point up to Polaris. So that's kind of what is going on there. In the southern hemisphere, not quite so lucky to have a pole star. They just have a general region of space that is the celestial South Pole. And so what they do is to take the Southern Cross and go about 4 lengths of the Southern Cross. 1, 2, well, let's see. I guess that's about 4 to find the region of space. And in this case, just in case you ever make the trip down there, the stars are going to go clockwise instead of counterclockwise. Cool. All right. So here is a busy slide. It seems like sometimes I don't think I brought my props along. No. So here's the deal. I think this figure will work for us. It's kind of busy. I'll show you what it's got going on. For example, let's pick August 21st. Well, that's not too far from now, is it? So we know that the Earth is orbiting the Sun. It will complete one orbit in 1 year's time. So tonight, though, if you look up at nighttime sky, you will see these constellations. Does that make sense? Because you have to turn away from the Sun before you can see constellations. So that, in general, is kind of what we have going on. Okay? The Sun appears to move, for August 21st, the Sun appears to move against these background stars. So if we're right here, we're looking at where the Sun is, and it looks like it is moving through these constellations. Now, I lose track of the whole, horoscope thing, but your horoscope should be related to where the Sun appears to be passing through. Okay, so for this time of year, it would be Leo, is your sign. Okay. If we look at November, we could do a similar thing. I'll change colors here. In November, okay, notice that our nighttime sky on the, if you want to think of it, the celestial sphere, if you want to think of it like in reality, we have relocated in space as we're orbiting the Sun, and we are privy to a different set of stars. Okay, so those would be kind of when the Earth spins to nighttime, those are the ones we're going to kind of see in the nighttime, kind of the middle of the night. Okay, in this case, it looks like the Sun is passing through Scorpius. Okay. Again, I will plead ignorance to the whole horoscope thing. One thing I want to point out, I did introduce one more slide for this topic, but I have never, run into anybody who said my sign is Ophiuchus. But scientifically speaking, okay, they're about, and actually my birthday is December 1st, so actually they're in the region of December 1st, that's where the Sun appears to be passing through against those background stars. We don't see Ophiuchus, okay, because this is what we see at night. But along those lines, here's a table Oops, need to let you finish in that. Here's a table of the constellations that the sun is passing through, okay? Again, I mean, we can't see the constellations because it's bright, right? But what it's passing through, and yeah, Ophiuchus is December 1st through December 19th. And this is sometimes where I get feedback from students, it's like, oh my gosh, they totally ruined my whole horoscope. So, science. Okay. What's that?
That changed his sign.
Did it change your sign? Dang it.
Mine, I missed mine by a day.
So it was okay? It didn't change your sign?
No, yeah, no, it changes mine by a day.
Mine's the same.
That's just not right. How many people's did it change? So just don't worry about it. Hey, why don't we, the next topic's seasons, and let's get a running start at seasons on Friday. So let's go ahead and for the day. Hey, any questions about Thursday though, tomorrow? That remember, if you want to get lab credit, you have an opportunity